Welcome to the second video lesson on circuit analysis, where we look at how to solve NSC style questions on matric level for circuit electricity. So in the first video lesson, we covered the basic definitions that you could be asked, like for instance on EMF, which is asked in this question, and power. We also looked at using the rail format in order to transform your circuit into what I believe is a visual format that makes it easier to analyze what is going on in the circuit. However, different teachers have got different ways of teaching this, and I'm not saying that my way is the best way, so I'm just sharing the way that I approach solving electrical circuits with you. I find it works for me, and as I've mentioned, I'm a visual learner, so I find that putting it in that format helps me to see what is going on in the circuit better. So I'm teaching from my approach, and I totally respect other approaches as well. And you, as a learner, as a student, you need to look at what works for you, because different students, different learners learn in different ways. So without further ado, let's take a look at this problem. So a battery with an internal resistance of 5 ohms and an unknown EMF is connected to 3 resistors. So we've got resistor 1, which is in series with the battery. If we follow the conventional current out of the battery, we see the total current go through resistor 1. It's certainly going to split when it goes through resistor 2 and resistor 3. So these two resistors will be in parallel, and then the currents will rejoin. Of course, that will only happen if the circuit is complete, when the switch is closed, and then the current will flow through the internal resistance of the battery and will continue to flow as long as the switch is closed and the battery is functional. So the first question is to find the term EMF of a battery, and we've already dealt with this in the previous video lesson. The EMF is the maximum energy that is transferred to charge in a battery per unit charge, or the maximum work done to charge per unit charge in a battery. So that is basic theory. Now, what I'm going to do is I'm going to quickly transform this drawing into Rails format, and I'm going to do it much quicker than I did in the previous video lesson. So I'm going to start here, and I'm going to draw the positive terminal of the battery on the top and the negative terminal on the bottom. Then I draw 2 rails. I'm going to draw a positive rail there. I'm going to make it a little bit bigger. I'm going to draw the negative rail or ground rail down here. And then the internal resistance here, I'm going to put inside the battery. So I'm going to put it, doesn't matter whether I put it below or above, basically represents the total resistance of the battery. So we just pop it in there. It's good to put the actual value in. Little r is 0.5 ohms. Right, we do not know what the EMF is. Right, then I'm going to go along there. We hit a resistor. So we are going to always put resistors when using the Rails format. We're going to put resistors between the rails. So this is going to be resistor 1, and that's going to be 4 ohms. Then as we continue to follow, we see that we hit an ammeter, and then we encounter these 2 resistances. So I'm going to do that. I'm going to put an ammeter in there. We're going to go there. We're going to have an ammeter. So that's going to be A. Then we're going to have the two resistors, resistor 2 and resistor 3 there. Right, we put their values in. Resistor 2 is 25 ohms, resistor 3 is 15 ohms, resistor 2 is 25 ohms. So we now then, they connect again, the two branches connect, and then there is a switch. But now between there and there are no resistors, so that's on the ground rail. So what we do is we just connect it again, and there we go. The switch can be on the ground rail there. Important thing is the switch can break the circuit. And so we now have the ammeter in the circuit. We have yet to do the voltmeter. The voltmeter, if you look at the voltmeter, this connection is on the positive rail there. And this connection here is on the negative rail, which is there. And notice that they are both on this side of the switch. So this is going to produce a reading even if the switch is open. So I'm going to put the voltmeter there. I'm going to just add, put it in another color, representing another color just to make it more visual. Right. And we have the rails format. So you can see it doesn't have to take too long. Something I just would like to mention is, let's assume the operational voltage. There's a reason why I'm doing this. I'm just going to assume, and then I'm going to retract. Let's assume the operational voltage here was, let's say, 12 volts. Then we talk about the positive rail as being, well, that would be plus 12 volts. All along there would be 12 volts, that the voltage wouldn't change along that rail. There are no loads to change the voltage along the rail. And we would say that the ground rail, this is now we're assuming now that this would be closed, that the ground rail would be 0 volts, and this would be 0 volts, this would be 0 volts, this would be 0 volts, this would be 12 volts, this will be 12 volts. Right, now, we call this the ground rail. We call this the ground rail. Rail basically meaning conductor. And this would be the positive transmission rail. However, I have a question. But this is the negative terminal of the battery. So isn't this the negative rail? Well, yes, it is. You see, we could say that this, and this is my point, this is negative 6 volts, and that's plus 6 volts. This is negative 6 volts, and that's plus 6 volts. You see, when we deal with voltage, we're dealing with the difference in potential. So the difference in potential between this rail and that rail, 6 minus negative 6 volts gives us 12 volts. That still means that when the 1 coulomb of charge goes through this battery, it's energized with 12 joules per coulomb, irrespective of whether we call this negative 6 volts and that positive 6 volts, or 0 volts and 12 volts. And so it's easier for us to define the ground potential as 0. Then we only need to work with positive values, and we don't need to work with negative values. But in actual fact, the ground rail is the negative rail. So I wanted just to clarify that, and I'm going to retract that, and we're going to move forward. So now we look at 8.2. It says the reading on the voltmeter decreases by 1.5 volts when switch S is closed. Now, give a reason why the voltmeter reading decreases. Well, that is because of the fact that as soon as switch S is closed, this is going to mean that current is going to flow. So we're going to get that I is going to flow, which means that we're going to get lost volts, because lost volts is I total times the internal resistance. which means that V operational, which is what the voltmeter is going to read, is going to be the EMF minus the lost volts. Now, prior to switching the switch closed, there were no lost volts because there was no current flowing, so therefore the operational voltage was the EMF. It wasn't the true operational voltage because the battery wasn't operating. But as soon as your battery operates and a current is drawn, whatever the internal resistance is multiplied by the total current going through the circuit, you're going to get lost volts. And those lost volts are going to take away from the EMF and give you an operational voltage, which is less than the EMF. Now, we are told that this is 1.5 volts. Now it asks, calculate the following when switch S is closed, the reading on the ammeter. Now, the ammeter is going to read the total conventional current. So if we look there, let's go to my redrawn circuit diagram. If we look here, the total current is going to flow through like that and through the ammeter. So this ammeter is going to measure the total current. But the total current also flows through the battery. It always does. So, but we have the lost volts, so we can work out the total current by working with what we're given. So this is now 8.3.1. We can say that V lost equals I total times the internal resistance. We know that the V lost is 5 volts. We are looking for the total current, and we were given the internal resistance. The internal resistance is 5 ohms. So we now have that this is 5 ohms that we put in there, 5 ohms, and now we divide both sides by 5. So 1,5 divided by 5 equals I total. And so therefore the ammeter is going to read 3 amperes. There we go. And if we look at the mark allocation, it's 3 marks. So I think that's quite, with confidence we can say 1 mark for the formula, 1 mark for the substitution, and 1 mark for the current, the actual current, the answer. I would like to just mention about subscripts. Now, in marking NSC physics, which I do, you don't have to put subscripts in there. When we mark, we look to see whether you have used Ohm's law. So you could have V equals I little r. But be careful if you put a big R there, because then you run the risk of losing that mark. So I would prefer you to use subscripts, because especially when you get to complex problems like this, where you've got many different voltages, because you've got different components with volt drops across them, I would strongly suggest that you use subscripts to keep track of what you're calculating. There's another benefit to it, is that when you do that, you make it easier for the marker to see what you're doing. And so it's got a double benefit. So now let's move on to the next part. It says, calculate the total external resistance of the circuit. Now, that's for 4 marks, but this really is marks for jam, because this year, 8.3.2, is really not difficult. And the reason why I say that is that from grade 9, grade 10, you would have worked with series parallel circuits. And so you would have done this before, long before grade 12. So first things first, we're going to work out R parallel, the equivalent resistance of R parallel. It's always good to start with the parallel part of the circuit. So I'm going to use the fact that R parallel equals R2 times R3, the product of the two resistors over the sum of the two resistors. Now, I specifically and explicitly state two resistors. You may only use this for two resistors. You do not get this formula on the formula sheet. You get the reciprocal formula, 1 over R parallel equals 1 over R1 plus 1 over R2 plus 1 over R3, etc. But you can use this. This is acceptable. So now we've got R2 is 25 ohms. So this is 25 ohms times R3 is 15 ohms over 25 ohms plus 15 ohms. So therefore R parallel is going to be 25 times 15 divided by 25 plus 15, which is 40, and that gives us 9,375 ohms. And you should be able to see clearly that this 9,375 ohms is smaller than the 15 ohms and the 25 ohms, which is what it should be because the parallel circuit has got an extra conducting path. So therefore, R external, the total external resistance, is going to be the resistance R1 plus the parallel resistance, and that is because of the fact that the total current runs through R1 and then goes through the parallel network, which is represented by the equivalent resistance R parallel. So R parallel and R1 are in effect in series, so we add them together. And therefore, we can say that R external is equal to 4 ohms plus 9,375 ohms. And adding those together, we get that R external is equal to 13,375 ohms, and that is the total external resistance of the circuit. So if we look now at the mark allocation, it's 4 marks. So I would surmise that there would be 1 mark for the formula for R parallel, 1 mark for the substitution, 1 mark for what R parallel is equal to, and 1 mark for adding the R1 and R parallel together to give us the total external resistance, that giving us 4 marks. So we now move on to 8.3.3, which asks us for the EMF of the battery. Now, if we look at what we already have, we have the total external resistance, which we worked out to be 13,75 ohms. We have the total current, which is 3 amperes. And we have the internal resistance, which we've also been given. It was given to us in the actual question. There is 0.5 ohms. So in order to work out the EMF, it's a reasonably straightforward thing to do, because if we look here, and this is 8,3,3, it's always good to make sure you number your solutions according to the numbering system of the question. So we're looking for the EMF, so the EMF is going to be I total times R external plus the internal resistance. And so this is the formula that we get off the formula sheet. We are looking for the EMF. We have I total is 3 amperes. R external is 13,375 ohms. The internal resistance, as we've already mentioned, is 5 ohms. And so therefore the EMF we can work out quite easily. We just work out what's in the bracket first, 13,375 plus 0.5 gives us that the total resistance of the whole circuit, that's the external resistors, and the internal resistance of the battery is 13,875. We multiply that by the total current, which is 3 amperes, and we get an answer of 41,625 volts for the EMF of that battery. So now looking at the mark allocation, we see that that was for 3 marks. So if we look here, I would assume that it is 1 mark for the formula, 1 mark for the substitution, and 1 mark for the correct answer with the correct unit. So we now move on to 8.4, and here we start to move into the conceptual questions, because as I mentioned in the previous video lesson, you tend to start off with a definition or 2, which is level 1, and then you start to go into the level 2 and level 3, which involves the actual circuit analysis using calculations, formulae, and doing the calculations. And then toward the end of the long question, you start to hit the upper level 3 and level 4 questions, which involve testing you on your deep understanding of the concepts. So this question asks, 8.3, a learner makes the following statement. The current through resistor R3 is larger than the current through resistor R2. Is the statement correct? Choose from yes or no, and then explain the answer. So that explain the answer now makes it a descriptive question, which raises it from, say, a level 2, which is an insight question, to a level 3, at least a level 3, where now you need to construct a description. So looking at R3 and R2, R3 and R2 are both sitting in the parallel part of the circuit. Now, looking here, because they're in parallel, if we were to place a voltmeter, here, and that voltmeter measured the volt drop across the parallel part of the circuit, then by now you should know that the volt drop across R2 and the volt drop across R3 is equal to the volt drop across R parallel. So when resistors are in parallel, the volt drop across them is the same. The current will split, but the volt drop will be the same. As opposed to when resistors are in series, we know that the current doesn't split, but the voltage does, because we add the voltage across each of the resistors in order to get the total voltage. So we can see that resistor R3 is less than resistor R2. So to get the same voltage, one would need to have a current that is bigger than the current through R2, because R3 is smaller than R2. So invariably, that's from a mathematical perspective. But generally speaking, the smaller resistor draws the most current, and the bigger resistor draws the lesser of, or the least current. So now we can say, well, let's look at the statement again. Is the statement correct that the current through R3 is larger than the current through R2? And we answer it directly, 8.4. We say yes. Okay, so that's 1 mark. So we've got 1 mark out of 2. Now the question is, how do we answer this? Well, there's different ways of answering it. But what we can say is, one of the things we could say is that the volt drop across R2 and R3 is the same. because they are in parallel. Okay. Hence, I2 is going to be smaller than I3 because R2 is greater than R3. And to really make sure that you get the marks, and I2 times R2 must equal I3 times R3, which equals V parallel. So I'm not saying this is the only acceptable answer, but I believe that if you had to answer it like this, you would get the 3 marks. So now let's look at 8.5. The 4 ohm resistor is now removed from the circuit. How will this affect the EMF of the battery? Choose from increases, decreases, or remains the same. Now, notice that it is only 1 mark, so it's not going to be as complicated and as complex as 8.4. And you probably can answer this question without even looking at the circuit. But let's look at the circuit. So if we were to take the 4 ohm resistor from the circuit, so we take this resistor out of the circuit, well, what's that going to do to the total external resistance? Well, it's going to reduce it. There's going to be less resistance, so it's going to reduce the external resistance. What would that do to the current? Well, it would increase the current. Now, how would that affect the voltmeter reading? Well, if we are increasing the current because we're decreasing the external resistance, taking this out, so it's only that resistor now in the external part of the circuit. Of course, this would be closed. You wouldn't have current flow if there was an open switch there. So if now your resistance is, external resistance is decreasing, then as we've learned in the previous video lesson, your total current would increase, which would mean that your lost volts would increase, which means that your operational voltage would decrease. But wait a minute, the EMF is not what's being read on this voltmeter when there's a current flowing. The voltmeter will be reading the operational voltage. And the bigger the current, the bigger V lost, I total times internal resistance. But the EMF is not dependent on that. The EMF is dependent on the chemical potential energy in the battery. The EMF is dependent upon the nature of the chemicals in the chemical system of the battery. So the answer should be to this question that it remains the same because the EMF is not dependent upon what's happening on the outside of the battery. The EMF is dependent upon the chemical system inside the battery, as we learn about when we do galvanic cells in electrochemistry. So I hope that this second video lesson has helped you to practice and gain a deeper insight into what we covered in the first video lesson. And in the next video lesson that follows this one, I will do another past exam question that involves circuit analysis.